Good, we good. Alright. 10.1.
Everybody do your homework. It's only 3 questions.
Difference of proportions. Okay, so we did, so chapter 7 was a chapter on sampling distributions. Chapter 8 was a chapter on confidence intervals, and chapter 9 was on hypothesis testing. The general format of those was theory, proportions, and then means. Chapter 10 is about comparing 2 different sets of data of the same types of things. So 10.1 will be about proportions. So we have one set of proportions comparing against another set of proportions. So like when you do an experiment, does my control group match my treatment group? Make sense? And we're only going to have 2 sections. Section 1 is on proportions. Section 2 is on means. And in the whole section, we're going to cover sampling distributions, confidence intervals, and hypothesis testing, because it's pretty much a repeat of the last 3 chapters with just small tweaks, which is why I said if you don't understand chapter 7, we're in trouble, because 8, 9, and 10 all build on it. Whee! But if you did understand it, you golden. This will be great. All right, so let's talk about the sampling distribution. We can compare 2 populations and find out how different they are. So we can do like the shape center spread. If you see like describe the distribution, p hat 1 minus p hat 2. So the shape is normal. If, okay, what was the normal condition previously with proportions, with p?
NP greater than 10.
Uh-huh.
And N times 1 minus P greater than 10. And then
So you're giving me the formulas for 10 successes, 10 failures, right? NP is greater than 10, and 1 minus P is greater than 10. Yep, same thing. This time it's going to be N1, P1, greater than 10. N1, 1 minus P1, greater than 10. And N2, P2 greater than 10. N2, 1 minus P2, greater than 10. So we're looking for 10 successes and 10 failures on both populations. So when we tried it on both groups, we had to have 10 successes and 10 failures. So it's not 10 successes and 10 failures combined. You can't get like 5 and 5. You got to get 10 in one, 10 successes in one, 10 failures in one, 10 successes in the other, 10 failures in the other. So at minimum, you're running 40 trials. Right? And that's assuming a 50-50 shot. Your center. Super easy. The average p hat 1 minus p hat 2 is going to be p1 minus p2. Surprise! Because it's not always, you're not always going to get the exact difference, right? So like if I go sample guys and girls, if they like the Crispitos at Navasota High School, no, let's do something different. Junior high and high school kids, right? Like, do you like Crispitos? Yes or no? And high school kids are like, they're a little greasy.
Yeah.
But the junior high kids are like, yeah, that stuff's awesome, right? So, so the difference of my statistics, the average difference should be about the same as the difference between the populations of high school minus the population of junior high. But it won't be exact, right?
Yes.
Does that make sense?
Yeah.
That's why there's an average difference. Because sometimes it'll be a little more, sometimes it'll be a little less. But it should be pretty close to that. How far off can it be? That's why we talk about, what's the next one?
Spread.
Spread. And so, if n is less than or equal to population n divided by 10, the difference, standard deviation of p hat 1 minus p hat 2 is equal to square root p1 1 minus p1 over n1 plus p2 1 minus p2 over n2. Hey, that's a cool formula. Did you just make it up? No, I didn't just make it up. I got it off the formula chart. See, because it says on the formula chart, are you ready to look?
You see it?
You see it on the formula chart? That is very shiny. See, it says difference of sample proportions. Now, we're not making the assumption that P1 is equal to P2 because we're not saying that we think that junior high kids and high school kids have the same interest. We just want to know how far off will our samples be, right? Right, so we're not making the assumption that P1 is equal to P2, so we can't use this easier formula. Oh, that would be too nice. So what we got to do is we got to use this one. But we got to use the bigger one. Make sense?
Yep.
Yep. Later on, though, we'll come down and use this one. All right. Okay, that's all you got to know for the sampling distribution. If I say describe the sampling distribution, there's your SCS. Shape, center, spread. Good?
Yeah.
Okay. My goal today is to cover all the theory in 10.1 and to have 2 full days of practice troubleshooting. Doing practice problems, troubleshooting, answering homework questions. Tomorrow we practice problems, and the last day I hope is troubleshooting and some troubleshooting before the quiz. So that's my goal. Practice problems tomorrow, troubleshooting the next day, and troubleshooting before the quiz. Okay, let's talk about confidence intervals. Let's do our conditions. So like when we do our plan, right? What are our conditions? Random. So for random, we're going to take an SRS of both populations. Which totally makes sense. You can't be biased on one and not biased on the other and expect it to be a good result.
Normal.
So random, SRS both population. Normal. We're going to be looking for 10 success and 10 failures. For both samples. And for this one, we're going to use real successes. and real failures. At this point in time, it'd probably be good for us to actually discuss what we're trying to estimate. Right? So let's go. Are you okay with me doing the junior high school Crispito thing? Okay. So if I go, let's say I go sample, and I sample my junior high kids and my high school kids, and we'll post-it note this thing up because I don't really want to mess my theory notes up with data. But we post-it note this up, and my X1, N1. So we'll say this is high school, and then we'll do X2, N2. You don't have to write this down if you don't want to. This is just me talking. This is junior high. Okay, so let's say, how many students you want to ask the high school?
50.
50. And how many of them do you think say like, yeah, like Crispitos?
23.
23. Cool. And then we asked
65.
65 at the junior high? Right? And how many of them do you think like Crispitos?
42.
42. That sounds great. Okay, so so there is a difference, right? Y'all agree with that? Okay, so what I'm wanting to find is the best, is the actual difference of proportion of high school minus proportion of junior high. So there is a true difference, but I do not know what that is, right?
Yeah.
Because I could have gotten high or low on the high school. I could have gotten high or low on the junior high. Right? If I got high on both of those, then I'm probably pretty close to the difference. If I got low high or high low, then I'm be more off. Right? There's a lot of variability on this. But what I'm trying to estimate is the true distance between the difference, or the true difference between high school and junior high's likings. Does that make sense? Yes?
Yes.
Okay. So, but am I assuming that they're equal?
No.
No, there is no assumption that these two populations are equal to each other, right? So that is why I'm using my real successes and real failures. Because I'm saying when I really did the survey, did I get 10 successes? Yes. Did I get 10 failures? Well, 50 minus 23, yeah. Did I get 10 successes?
Yes.
Yes. And did I get 10 failures?
Yes.
Yes. So I'm good on those conditions, right? And so you can either say, you can either tell me how many successes and failures for each, or it's probably one of the easiest ways, or you could say at least 10 successes, 10 failures for both, whatever. Yes, ma'am.
Were we not doing that for the last one?
For the last one, for the last chapter, you were only doing for one proportion. So I would say, like, for the last one, I would say what someone's claiming that 65% of high school students like Crispitos, and you found that 23 out of 50 like them. What's the probability that less than 65% like them? Right? Now the claim is going to be the cafeteria manager is claiming that the percent of students that like Crispitos is equal on both campuses. You think that they're different. So you're going to have you're going to wonder if 0 is inside this interval. Because you're going to think that the distance is not, the true difference is not 0. Because you think that when you subtract the two, they won't come out to be 0.
I was talking about the real successes and failures.
Oh yeah, you did that last time on confidence intervals. But you don't do it on hypothesis testing. For confidence intervals, you use real data. We're good? Okay. All right, independent. And we're going to use the same one. N is less than or equal to n over 10. All right, for the do. Okay, we're going to have our formula. The formula for confidence interval is going to be this. And I'm going to write, yeah, I'll do that. Okay, it's going to be a statistic plus or minus critical value times standard deviation of statistic. And so in red, I'm going to give you a formula above and below for each of them. So there's two different formulas you can use depending on what you get.
I have a question.
Yes, ma'am.
It says critical value, and then what is that? Times?
Times standard deviation of statistics. If you're looking for it, it's actually on your formula chart. I can show you right there. Confidence interval is statistic plus or minus critical value times standard deviation of statistic. What I'm writing in red is not going to be on your formula chart per se. The first one will be on p-hats, if you just have your p-hats. So it'll be p-hat 1 minus p-hat 2, because this is your statistic difference, right?
Mm-hmm.
So there is a difference in the proportions. Plus or minus. Now, with p's, we talk about what letter? Z's or t's? Z's. So it's going to be a z star. Now, our formula has p's, but if I knew what p was, it'd be silly for me to have a confidence interval about it. So what is my best guess for p1? P-hat 1, right? Does this make sense?
Yeah.
Okay, look. Those of you that are not following this, see, my formula says P1. But if I knew what P1 was, I wouldn't need an interval for it. So it's kind of stupid to say that we're going to use a formula to guess something, because if I knew it, I wouldn't have to guess. I'd just tell you what it was. Right? So my best estimation for P1 is P-hat 1. And my best estimation for P2 is P-hat 2. So I'm just going to write that same formula that's on my formula chart, but I'm going to substitute P-hat 1 and P-hat 2 in for those So P-hat 1, 1 minus P-hat 1 over N1 plus, and you know your calculator is going to do all of this when you just type it in. It's going to be one lovely. So we're not really worried about filling in the numbers. Just letting you know how this stuff's going to play out. Okay. Now, this is your basic formula, but sometimes you're given successes and trials. Right? We tried this. We tried it like this data. With we asked 50 people, we got 23 successes. We asked 65 people, we got 42 successes. Right? And do you have to convert this into p-hat 1s? No, you don't. It's wonderful. So if you don't want to do that, you can do this. X bar 1, or x1 over n1 minus x2 over n2. And then z star. And then square root of x1 n1 1 minus x1 n1 over n1 plus x2 n2 1 minus x2 over n2 all over n2. So either of these will work, depending on what information they give you. And all I really did was just substitute x over n for p hat. So they're the same. Okay, I got. Just doing good on time. Got about 20 minutes left. We got cover hypothesis testing. We'll be done for the day. I don't know if I can cram much more information in to your brains.
Wait, can you show us on the calculator?
Show you on the calculator. It's super easy. Sure, I got time for that. Meow. I'm gonna have to do this on the calculator Zoom. Whee.
Are we doing P hat or X?
So it's statistics, confidence interval. Which one am I doing? Come on. Two prob Z interval. Woohoo! We'll use our data. 23 out of 50, 42 out of 65. Let's find a 99% confidence interval for the difference. There we go. My lower, my upper, my p hat difference, which is p hat 1 minus p hat 2, right? Yep, there's my p hat 1, there's my p hat 2.
Okay. So
There's everything. If you scroll up, there's all of that. It's good, right? Yep.
since 0 is what you're doing?
Since 0 is not in there, if I was actually doing a real thing, I would say, this is my 95% confidence interval. There's reason to believe that these groups are different. You probably shouldn't believe that cafeteria worker, manager, whatever. You probably shouldn't believe the manager that says that they both like them equally. There's probably about a 19% difference, 18% difference, because that's my p hat diff.
Yeah.
Yes.
Yeah.
Not to be disrespectful, but you know, just. Oh, turn the light on. No. Did that adequately address your concerns, calculator-wise? It's so easy, isn't it?
Yeah.
I mean, all we really have to talk about is the conditions in the formula, because like your state's the same, your conclusions. Like I just discussed the conclusions, and you're like, oh yeah, because I knew the sentence. If you know the sentences, like we're good. Let's talk about hypothesis testing. Still gonna have our HOs. We're still gonna have our HAs. It's gonna be great.
This is a lot you're cramming.
I'm telling you, we're doing like 3 chapters worth of updates, just because there's 2 variables instead of 1. It's great. Hypothesis testing of differences.
How much of a page is this going to take?
It's going to take up this much of a page.
Oh.
So 3/4, 2/3, 60%, 55%. Okay, so if we're doing this, we'd do our state. We'd have HO. And the reason it's going to take a lot of space is just because I'm going to try to give you just a blueprint, right? Or like a blank outline. I feel like it'd be useful for this. P1 is equal to P2. Okay, so we are going to assume, this is very important. This is very, very important. You need to listen to me. The assumption here is that P1 is P2.
Okay.
The population proportions are equal, and when you sampled, although you found a difference, that just happens because life is random. You're assuming that the 2 proportions are equal to each other. In the confidence interval and the sampling distribution, you did not operate under that assumption. Right? You're in full awareness that they are probably different from each other. But in the hypothesis testing, you are assuming that they are equal to each other. Just like we assume like you're innocent until proven guilty, right? In this, we're assuming those 2 proportions are equal to each other, and it's going to change, it's going to tweak how we do some things. Okay? All right. So now we're going to say HA, P1, and then we're going to have a blank, P2, it would be not equal to, greater than, less than, determines the size of your testing. You'll draw your picture accordingly. You also have your definitions. P1 is blah, 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 blah. P2 is blah, blah, blah. You need to have those listed. You need to tell me what they are in real words. In real words, you need to tell me what those are. It's part of your state. You're stating what P1 is. You're stating what P2 is. Okay?
Yep.
There is a last piece that is very important. You need to tell me what your P hat C is. Huh? It's x1 plus x2 over n1 plus n2. Okay, we're going to talk about this. x1 plus x2, n1 plus n2.
And then it's PC hat.
It's PC hat. It's proportion of combined. It's your P hat combined. Okay, what this is you are assuming that P1 and P2 are equal proportions, right?
Yeah.
Yes? So, the best guess for P1 and P2 is not either the sampling from P1 or the sampling from P2, but rather the combined data, because it's the same proportions of people. Right? So, for example, if 57% of the junior high kids like Crispitos and 57% of the high school kids like Crispitos, the best guess for who likes Crispitos is not going to be the 23 over 50, and it's not going to be the 42 over 65. It's going to be all the yeses I got over all of this. Because what the manager is going to say is, no, these groups are equal, so what you need to do is say, you actually talked to 115 kids. How many total of the 115 really liked it? Because they're equal. Stop splitting them into two groups. Does that make sense? So this is my best guess for what it is, not either one of these. Make sense? Because we're assuming that they're equal. Because we're giving them the benefit of the doubt. Plan. For random, both need to be an SRS. For normal, okay, we're going to have 10 successes, 10 failures, but we must have, I'm going to write it out. So we must have P hat C times N1 greater than or equal to 10. Oh, 1 minus P hat C times N1 greater than or equal to 10. P hat C times N2 greater than or equal to 10. 1 minus P hat C N2 greater than or equal to 10. This is 10 successes and 10 failures. But you're not using 10 successes and 10 failures in any other way you have before. It's not 10 successes and 10 failures on what you think P1 is, or what you think P2 is, or what you found. It's on the combined information, because the combined information is your best guess if you think that they really are equal. So you're going to get these odd numbers that you haven't seen before. Does that make sense? And for independent, we're going to say that n must be less than or equal, sorry, n1 divided by 10, and n2 less than or equal to n2 divided by 10. And I don't know if I put that on the other page. Oh, I didn't. 1, 1, yeah, go back. n2 less than or equal. There we go. So on the other one, sorry, I didn't put 1 and 2 on my independent. So this is on the confidence interval. Made it 1 and 2. Because you got 2 samples, right?
Mhm.
So if the high school has 800 kids and the junior high has what? 600 kids?
Sure.
Sure. Hopefully I have 650 because I sampled 65. Yeah, you know, there's some growth as kids move up. All right, do. All right, Z equals okay. Was it helpful to have the words before?
Yeah.
Yes. So if I take a little bit more space and show you the words and then step it out, you okay with that?
Mhm.
Okay. So it's statistic minus parameter over standard deviation of statistic. There are 2 ways to find Z. Depends on what information you have. Or how you want to do it. First, we can just use the p's. So we can do p hat 1 minus p hat 2. This is my statistic. If you are a highlighter person or a coloring person or whatever, I don't know how to visually represent this to you, but all of this is my statistic. Okay? I have yet to enter the parameter realm. This is my statistic. So however you want to indicate that, you want to like draw a little box up here or something like that. Now the formula is going to be minus 0. And the 0 is my parameter. What in the world? That is stupid. Why did you just write a 0? That's not a formula thing. Well, actually, I am glad that you asked.
You said 0 is your parameter.
That's my parameter. This is my parameter here. Oh, I can guess I can. You want me to write up here like stat? So if you're ever looking back, parameter. There we go. Let me show you how we get this 0. Have a little dream.
Would it always be 0?
The 0? It's not O, it's a 0.
No, yeah, I'm saying would it always.
Let me show you how we get it. It's always. Let me show you how. P1 is equal to P2. Right? So if I subtract P2 from both sides, should get P1 minus P2. And then this side would be 0. So,
But that would still be 0?
now this thing, do I know P1? This thing, I do not know. I don't know how many kids like Crispitos in high school. And I do not know how many kids like Crispitos in junior high. But I know 0. Right? So of all the things I know, 0 is what I know. Yes? So I don't know P1, I don't know P2, I do know 0, so I put 0 in the formula. We good? Oh. That was a nice little dream. Alright. all over square root of, now standard deviation of statistic, we come back over here to the formula chart. You see difference of proportions? There's a special case. When what?
When P1 is equal to P2.
P1 is equal to P2. And it's, oh man, you have that one proportion. And what is that one proportion called for us? It's our P hat C, right?
Yeah.
Alright, so we're going to fill that in. So we're going to do P hat C 1 minus P hat C square root of 1 over N1, 1 over N2. So all of this is my Z.
Is it a times between the 1 over N1 and 1 over N2?
Oh, this is plus. I'm sorry.
Okay.
The other way that you could write it is just to change your p hats into be x over n's, right?
Yeah.
Right. And so the way that would look, for those of you who are wanting things a little more complete, would be x1 over n1 minus x2 over n2 minus 0 over square root of, now this p hat c is going to be x1 plus x2 over n1 plus n2, 1 minus x1 plus x2, n1 plus n2, square root 1 over n1 plus 1 over n2. Now some of you say, Barrett, that's too much. Yes, ma'am. That's too messy, that's too much, I do not want to work that hard. But let me tell you why you would. Because I think I can make a pretty compelling argument as to why you would want to write this down. The AP test, if you have a calculation error, they will follow it with you. The further you show your work, the better off you are. So, if you just write this up here, and you never show them how you're getting all this, then they can't follow it, right? But if you actually just write all this stuff down and then just give them the z-score your calculator kicks out, then they know that you knew exactly what to put in all these places, and you just had a calculation error on your z-score, and now they'll only dock you points on getting the wrong z-score, but everything else you'll get correct credit for. That make sense?
Yeah.
Okay. Okay, that's all I got today. You got like 2 or 3 questions on homework, so hopefully it's not too bad. Bye.